All right, everybody. I apologize for missing class yesterday. I had a family medical emergency, had to take a relative to the hospital. Everything turned out okay, but sadly we missed some of the material that I wanted to cover. So here's what I'm going to do. Today I'm going to come up with a video that talks about a few different topics that we need to know. You'll need them for Project 3, you'll need them if not for the midterm, then for the final. So we'll go through some of those, and my goal is to make these topics somewhat independent of what we will cover in class tomorrow, which is Wednesday, October 18th. So let's pick up where we were before. We have one more thing to talk about strings. And if you remember, we went through a whole bunch of different examples of strings. We showed how strings had length, that was there. They had position, which differed from length kind of by one. A string that had a length of 7 would have characters in positions 0 through 6 because computer scientists start numbering things at 0. We showed how you could compare strings using either the compare method or the greater than, less than, or equal to. And when those things are compared, they get compared by the ASCII value, which is the character code of their different letters rather than something else. So let's look at one other thing. What I would like to look at is something called substrings. On occasion, it is very useful to take a string and be able to separate out a little part. So I've gone back here in this program that you can see on the screen to kind of our basic string program where you enter a first name, you enter a last name, and it prints them out. And what I would like to show you is that you can take out part of a string and make a new string using the substring command. So let's try this. What we're going to do is we're going to create a new string, and we'll call it sub, which is going to be short for substring, and we're going to set it equal to first name dot substr, which is short for string. And this substring takes two numbers in it. They're called two arguments, and the arguments are where to start and how long to go on, how many letters to go on. So we'll say 2, okay? And what we will do is we'll output substring. So here's our algorithm for this program, right? Declare the variables that we're going to need to hold different things, output a message to the user that we're going to ask them for their first and last name, actually input their first and last name, and then output their first and last name, and now we're going to output substring. And in fact, let me just put something here so you can see what it is that we're doing. And we're outputting the substring. And substring, again, comes from the variable first name, substring 0, 2. So it should start in the 0th position and take 2 letters. So let's take a look and see how well that works. So I'm going to compile string6.cc .o string 6. And it compiled well, so let's run it. String 6. I enter the first name Clay, last name Shields, your name is Clay Shields, and substring is CL. If we go back and look at our program, it worked just fine. We said, hey, start in the 0th position and take 2 characters. And as you recall from strings, 0th position is the first letter because things are numbered starting at 0, and we take 2 characters, so that is the C and the L. 0th position, C and L. So there we have a substring, which is CL. So this is pretty useful, right? Because using substring and using at, you can take a string and break it down into component parts. Let's try a different one. Let's try making a substring out of my last name. Sub equals last underscore name dot substring str, and we'll start at, I don't know, 3 and go for a length of 4. Okay. We'll output that again and see what that does. So again, same algorithms before, but now after we've done the substring once, we're setting equal to the last name substring 3, 4 and outputting that. So make sure this compiles cleanly. It does. There's no message. Let's run it. First name Clay, last name Shields. And we see Clay, Shields. So CL we had the 0th position take 2, and we had the 3rd position take 4. So this is the 0th position is the S, first position is the H, second position is I, so the 3rd is actually the E, and if we take 4 characters, we get LDS. Okay. All right, so I hope that's clear, right? Substring. It takes a position. The position is exactly the same type of position in at. It is numbered from 0 up to the length of the string minus 1, and then a number of characters. Now the question might happen is, what happens if we take more characters than there are? So here I'm going to take, I just changed our little program here. Well, let's do this. I will copy this and we will do it all over again. So these are substrings. This is a test to see what happens when substring is too long. So we're going to go to the 3rd and take 14 characters. Okay? This last name substring 3, 14. My name is not in any sense 14 or more letters long, so we'll have to take a look and see what happens. So I'll clear the screen. I will compile. It compiled cleanly. We'll run it. First name Clay, last name Shields, and here's what we get. Clay Shields, CL, ELDS, ELDS. Now if you look, what happened is we got the same thing both times, even though in this case we told it to take 4 characters, and in this case we told it to take 14. Now why is that? Well, the reason is because it reached the end of the string, right? There wasn't anything after that for it to take. So even though we specified to take a longer substring, it was forced to stop when it ran out. Okay, so that's substrings. That's something that is a good thing to have on midterms and such. So that's good for that for right now. We'll talk about some other stuff in just a minute. Okay, I want to go back and revisit something we looked at a little bit earlier, which was how to read from a file. Now, if you remember, when we did this, we wrote this little program that included certain things. First of all, we included fstream, which is the library that allows us to do file input and output. We had a file name for a string, an input file of type ifstream. if is input file stream, and we had some numbers. And here's what we were doing. We were asking for a file name, reading the file name, opening the input file using the file name, which was converted to a C string using this .c_str. We needed to do that to make the compiler on CS class happy. Some compilers you don't need that, but some you do. Then we read a bunch of numbers, 4 numbers from the input file, and then we output what we read using cout to the screen. So let's go back and take a look at that. You can see I'm using the name filewrite.cc, which gives you a hint of where we are going on this one. We are going to look at how to do the same thing for writing to files. But first, let's just make sure this works. We do file write, and when we run it, sorry about that, and when we run it, we input a file name. We have this thing input.data, and you can see that something happened. We got 4 zeros there. Well, that's interesting. Let's take a look and see what file input.data has. Aha! There is no input.data. So what happened is when we went to do this input, the file didn't open correctly, so we did not get a chance to read the file. So what I'd like to do is show you how we can fix that, how we can loop in case file name is wrong. Okay? What we can do is we have something like this. You say while, and this is pretty tricky, not using the exclamation point, input file. So if you input file, if you put it as a Boolean, will let you know if it's open for reading or not. Okay? And so we can say while not input file, and we can repeat all these steps again. So I'm going to copy these, put these down here, put a little message as to what happened. And try to reopen the file. Okay? So let's look at our algorithm now, just so we understand what's going on. It's just like we did before. We ask for a file name. We input into the file name. We do input file open, filename.c string. And then we're able to do this check. And we say if not input file. And what that means is if we are not able to start reading from that file right now for whatever reason, we need to do what's inside this loop, because this loop executes when this is true, and it says not ready to read. So we output file not found. Please input a file name. We input another file name, and we try again. This should give us the opportunity to try over and over and over again for getting the right file. It's really helpful for the users. As you say, we humans are imperfect, and they may not remember, or they may mistype or something like that, and then they don't have to run the file again. So let's compile this and see if it works. It does, so let's run it. And I'm going to use the same wrong thing that I did before, input.data, and it says file not found, please input a file name. So it detected that this was a bad file name, and instead of running through and just outputting the initialized values, it says, hey, I didn't find that file, please try again. So let's give it the right name, input.data. And now you can see it actually found and output all of these different numbers. Okay? So that's very nice. Oops. So now we have this file, and we can, figure out when what the right file name is, and we can read from it. What I'd like to show you how to do is also output to files. Okay, this is inputting to files. We would also like to see how to output files. So if we have an IF stream, which is an input file stream, which is input file, we can also have an OF stream, which was an output file. And it's going to work pretty much like input file does. Once we open output file, we will be able to output to it. We will be able to use it just like cout. If we use IO manip, which I'll show you, we can format it and everything, but we just have to tell it where to go. So what we want to do is we want to just do everything here, but instead of outputting down here, we're going to ask for a place to write to. So we'll say cout, angle, 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 angle. Please input a file name to write to. Cn, and we can reuse file name because we still have it sitting around and we're not using it right now. We can say output file dot open, file name dot c underscore str. We still need that for the time being. And if we wanted, we could also do some other testing here, but in general, output files are less sensitive than input files. If an input file doesn't exist, the computer won't create random data for you to use, but if an output file doesn't exist, the computer will just open a new one and allow you to output to it. So we're going to do output file open, and now we can output what we read. And instead of using cout, what we can do is we can say output file, and all of these things will be output to the name of the output file that we go there. So again, to review our algorithm, we've just been modifying this one. Ask for a file name, open the input file. In case we screwed up about what we were doing with the input file, we have this loop that says, hey, I wasn't able to open the file, please give me a different file name until the file is open. It will then read from the input file into these numbers. It will ask for a file name to write to, which is for output. It'll open the thing for output, and it will output those numbers. You know what we're going to do, though, just to make this interesting, since we don't really need to write a file that orders numbers we want, we'll just reverse the order. So in this one, what we'll say is, everything came in 1, 2, 3, and 4. We'll write it out 4, 3, 2, and 1. So let's make sure this compiles cleanly. It does. Let's go ahead and run it and see what happens. So input.data. We'll input a file name to write to, and I'm going to call this output in all caps. And that's it. Our program ran, and that's all we saw. Now you might be thinking to yourself, wait a minute, where did all the numbers go? Why didn't we see anything print to the screen? And the answer is because we didn't do any couts that print to the screen. Instead, all our output went to this thing, output file. Now, we can see what's in output file. We can use the cat command over here. I'm going to clear the screen, and we can do cat output, and it will show what was in there. And in fact, the 4 numbers that we saw reversed, which is what we expect. Okay? So we're able to read from a file, we were able to output and reverse the numbers. So I want to show you a couple other things. Well, let's just pause for a second. Any questions? No, of course not, because you're watching a video and I can't hear you anyway. So please bring questions to class, but here's what we did. We just used output file almost exactly as if it were cout. We can do other things with output file. We can say output file, we can do something like fixed, we can do set precision 7, for example. And so now we're going to run the program again. I'll compile it. And it says, oh, it doesn't know anything about set precision. Okay, so let me go back to my program up here, and I will pound include iomanip, because iomanip is required to use set precision even with files. And we will try doing that again. And this time it compiled just fine. Okay, so let's run it. Input a file name. This is the input file, so we input.data. Output file name, we use output. And again, no visible output to the screen because everything went to the file. We can see the contents of the file by running cat output and outputs. And we can see now that we are getting 7 decimals of precision, which is far more precise than we actually entered anything. Just like we use set precision, we can use, set width for some numbers and so on. Set precision, that's too many points, decimal points. So you can see that we can also use any of the iomanip functions in writing the output file as well. So 4 decimals, this was set width 12, this one, the other ones were not. So you can do whatever formatting you need to the output. So this is really handy, right? Because we don't always want to just output to the screen. Sometimes we want to output to the files, and output file allows us to do that. So bring any questions to class. It's really straightforward, right? All we're really doing is doing getting a file name, output file open, and then instead of using cout, using output file puts stuff into the file. It does not print to screen. So if you want to print something to the screen, you also have to cout it. So for example, we could do cout here and just copy this whole line and paste it back up here. And when we ran it again, we would see that it is printing to the screen as well as to the file. When we cat the file, we will see that it has the same thing. Now, you might say, why didn't the output here have all those zeros? That's a good question. It's because we only used fixed and set precision with reference to output file. We did not use it to cout. If we wanted the output to be identical, we would also have to do fixed and set precision for cout. Okay, so that's how to write to a file. Pretty straightforward. If you can read from a file, you can write to a file. Just use this output file instead of cout and set it up like I showed you up above. Okay, let's go back and look at something that you might have noticed when we were working with the writing output to a file before. I've gone back to our original file that we had for doing input from a file. And if you look, it's exactly the same it was. We ask for a file name, we get the file name, we open the input file, and then we read numbers from the file. How many numbers do we read from the file? We read 4 and exactly 4 numbers from the file, and then we output them. So this all works quite well, right? We have input, we have our 4 numbers, and we output. Let's actually make sure this is working. and then we will talk about how we can change this to make it better. So if we run this program, we say input.data, and we get the numbers in there that we got out. Or we get out the numbers that were in there, which is great. So there's one annoying thing about this program, and it is this. We have a file that has 4 numbers, and in order to hold those 4 numbers, we have to create 4 variables. What happens if we actually have more numbers in there? So let's add some other numbers, 8.9, 18.2, 14.7, 1592.3, 4, right? Now we have 8 things. If we want to read those, what we have to do is have 8 variables. And this gets really annoying after a while, right? Like you can imagine if we had 10, we would have to create 10 variables. If we had 100, we'd have to create 100 variables. In fact, if we had 1,000,000, which is not out of scale for what computers can do, we would have to have in our program 1,000,000 variables. Now, as you can guess, this is not very tenable, okay? It just doesn't work very well to expand things like that. So let me just finish up pushing us up to, 8 numbers here. We have 1, 2, 3, 4, 5. Our lines are getting long, so let's break them. 6, 7, and 8. So now we have, the same thing we had before, a file. We're reading 8 numbers instead of just 1, instead of just 4. And let's make sure this works. It does, sort of, but we only got 4 numbers out. What went wrong there? Oh, we forgot to read in those. So, okay, well, let's read in the numbers as well. Sorry, I changed them in 2 places. I needed to change it, but not all of them. 8, 7, 6, okay, 5. Now this will work, I hope. So now instead of reading 4 numbers, we're reading 8 numbers, and we're hating life in general because we have 8 different variables we have to hold things in. But, oh, come on. Oh, bad file name. See that little colon on the end? Try it one more time. All right, now we're getting all our 8 numbers out like we are supposed to. All right, the point of this whole thing is to show you that using individual variables to hold different numbers does not scale. It just doesn't work well when we have too many variables, right? What we need is a way that we can have essentially an indefinite number of variables that don't all have different names. You might think of it this way. You might think of it as if you were going to go to the store and you were going to buy 30 beverages, 30 cans of Coke, or when you get old enough, beer, or coffee drink, or whatever you hand. You don't just go to the shelves and buy 30 things at once and carry them around, right? That 30 cans is just not tenable. Instead, you put them all together inside something. And the thing that you put them inside is a container, right? It's a box, it's a bag, it's a carton, something like this. What I'd like to show you now, and what we're going to start using, is a container that can hold many different variables, all of the same type together. Okay? And we're going to work this out. This special container that can hold things together is called a vector. And so we do pound include, not capitalized, pound include vector, and now we can use vectors. And what we're going to do is this. We're going to declare a vector by typing vector. We are going to tell it what type it holds, like what the values it's hold. In this case, all our variables are doubles, so it's going to hold doubles. We give it a name, and we can call this numbers, which we read. And if you want, you can tell it how many it has to hold. So what we're going to do is we're going to transition from having 8 different variables to having one variable that is a container, like a box or a carton or something like that, that holds 8 different things. And this is pretty nice, right? We only have one name for it. We have numbers. And we'll show you in just a minute how we can get things into each of these. So we're going to use numbers instead of these variables. So I'm going to just get rid of that because we don't need them. Okay, so we ask for a file name, we input. Now, when we read from the file, we have to put the values into the right spot. And the way we can do this, there's actually a couple of ways, but the easiest way is just to put a square bracket like that with the slot you want to put it in. Okay? So, we'll do 0. We'll do 1. We'll do 2. We'll do 3. I should find a way to speed all this up. 4. We can break the line because it's getting too long. 5. We'll do even better than this. Just a minute. 6 and 7. Okay. So notice, just like a string, we are going to say this vector holds 8 different numbers. The numbers themselves are going to be doubles, and the position in the vector is going to be numbered from 0 to 7. Just like the string, we will have 8 things in it, but they will be numbered 0 through 7. Okay? So, I'm going to go ahead and finish typing this up. I might actually just cut this part out because it takes a long time. Anyway, when I come back, I will have all this done. Okay, so I'm back, and what I've done is I have changed things from num variables to these numbers 0, number 1, 2, 3, 4, 5, 6, and 7. So let's go ahead and actually see if this compiles correctly. It does. Let's make sure it works correctly. And indeed it does, though I forgot an inline right here. Okay. So here's what we're doing now. We're doing the exact same thing we were before, except instead of having 8 different variables, we have one variable, numbers, which is a vector. A vector, again, is a container or a box that holds numbers, and we're telling it that it's going to hold 8 numbers. And we can reference these things by 0, 1, 2, 3, 4, 5, 6, and 7. Like a string, they are numbered starting at 0 instead of 1, and we can do things. So now we can also do a couple other things. So one of the things that we could do is we could try and fix the fact that we haven't actually made anything better, right? When you remember before we had the vector, we had 8 individual double variables, right? num1, num2, num3 through number 8. Now, even though we only have one vector, right? We have number 0, number 1, numbers 2, number 3. We haven't made anything better. We still have to reference each one of these things explicitly by using these square brackets and that number inside. So let's fix this. Let's do better than this and make it easier on ourselves. So what I'm going to do is I'm going to copy this vector.cc file to vector 2.cc, and we will start working on that. So, because we're going to start making some changes here. So the first thing we're going to do is we're going to not tell it how many numbers we're going to use. We're just going to say vector double of numbers and not give it a parameter to tell it how big it is. The next thing we're going to do is we're not going to explicitly use all of these numbers 0, 1, 2, 3, 4, 5, 6, and 7. Okay? So here's what we're going to do instead. We are going to read from the file like we did for project 2. And what we're going to say is, well, input file into some temp num. Okay? And what we're going to do is we're going to loop through the file. Each time we're going to put the number in some temp number. And now what we're going to do is we're going to say numbers dot push back temp num. Now pushback is a special operation that vectors can do that means add this to the end. Add it to the end. So what you'll have is initially we'll have a vector called numbers that won't have any numbers in it at all. It'll be empty. But each time we read a number from the file, we stick it onto the end of the vector. Now I'm going to leave this part, the output, just the same for right now so we can see what the, to make sure that everything is still working, okay? Remember, numbers refers to the vector. The square brackets with the number inside refer to which place inside the vector, okay? So let me make sure that this is compiling correctly. Oops, I forgot to define what temp num is. So let's create a double variable named temp num really fast, and that will hold it. All right, so now we can go ahead and run the program. And so here's what we do. We run dot slash vector2. We give it an input file name, which is input.data. And look, it printed out 8 numbers, 1, 2, 3, 4, 5, 6, 7, 8. And these are exactly the same 8 numbers we saw before. But look, we didn't have to explicitly put them into the vector by position. We didn't have to say this one goes in the first, this one goes in the second. Again, what we did is we declared this vector of numbers. It is an empty vector. You can think of it like an empty box, an empty carton, an empty case, whatever works. And then we declared this temporary variable temp num, and every number read from the input file one at a time and put it inside the variable temp num. Then we used the pushback operation, which means add this to the end of the list or the vector or the container, and so it added it to the list. When we output it, we saw that everything was output just as we expected, right? Number 0 was the first thing that was added in there, was the very first number in the file. Numbers 1 was the second number, and so on. So we read all those. This is much more convenient, right? We don't actually have to explicitly put things in. We can actually just say, hey, add it to the end. Now, let's do the same thing with the output, because the output is also kind of annoying that we have to explicitly print out all of those things, okay? What we're going to do instead is we'll use a while loop, and we'll say position, we'll say int position equals 0, and we'll say while position is less than, and check this out, numbers dot size. So you remember with the string we could do length. Well, vectors has something called size. So numbers.size asks the vector, essentially, it returns how many elements are stored in vector. So what we can say is while the position is less than numbers.size, we can see out angle numbers square bracket position. And I need a semicolon there. Okay. Now, what's going to happen here is we have a loop, And it's going to say if position, which starts off as 0, is less than the size of the vector, cout numbers position, which is the thing in the 0th position of the first one. One thing that's important for us to do is to, after we've used that position, increment it so we get to the next one. So as we go through this now, we should see that we're going to output the same 8 numbers we saw before, but instead of referring to them explicitly as 0, 1, 2, 3, and so on, we're able to use this position variable, which changes over time. Because initially it's going to be 0, and then after we use 0, it's going to increment to 1, 2, and so on. So let's see if that works. And indeed it does. Though something has gone wrong here, right? You can see that we output all the things, but what we forgot to output was a space. And when we're done with all that, we would also like to output an end line so that our output will be cleaner. So we saw it worked, but let's clean up the output and do it nicely anyway. Input.data. And we have our 8 numbers, 12.7, 4.3, 3.2, 123.7, and so on. All 8 numbers. Now what's cool about this is, again, remember before we had to have 8 different variables. Now we have just one variable, numbers, that happens to hold 8 different things. We can access what's in there by using these square brackets for each position. So the first thing is in the 0th position, the second thing is in the first position, and so on. Okay, you may not have realized this, but this is actually super powerful. It's super powerful because before, while we had to have 8 different individual variables, now we only have 1. And the thing about this container is it doesn't matter if it holds 1 thing, or 2 things, or 6 things, or 8 things, or 100 things. We are no longer tied to that particular number. So what we might choose to do is we could edit input data, and we could make this, you know, as big, as many numbers as we wanted. And it doesn't really matter how big it gets because we're always going to have space, well, as long as we don't run out of memory in the computer, we will always have space for things. So I've just added the number of lines there. I'm not even going to count how many because it doesn't matter to us. If we go down here and we run the same program again, it got all of those numbers. And there were a bunch there. I didn't count how many. Okay? And this is super awesome. This is super awesome because now we are free of the tyranny of our old version that looks like this, where we explicitly had to number things. And now we have a setup like this one, excuse me. This, where now we only have one variable, one container that's holding a variety of different things. So, vectors are awesome. You can imagine for your project 2, where instead of having to deal with each line exactly as it came in, you could have put all of those lines into vectors and had them around and been able to refer back to them. You didn't have to lose them at the end of each loop iteration. Okay, so let me just switch over to some other stuff and I will show you some other things about vectors that are really useful. Okay, so I've created a new file here so that we can do a few things with vectors just to show you what's in there, okay? So let's just create a vector. We can call it a vector angle bracket of double. This is going to be a bunch of numbers that we can have in there, and we'll call it numbers again. Again, this numbers is just a variable name like any other. Vector is like a type, like int or float, except because it's a container, you have to tell it what it's going to be holding inside. So in this case, it'll be a vector of doubles. You could have anything here instead of double. You could have int, float, string, character, Boolean, whatever your heart desired. The vector can hold them all, okay? And again, this is a container that has a bunch of different stuff. So let's just, I don't know, let's go through and show you a few things. So one of the things that we can do is we can find out what size this is. So let's just see out numbers.size. And this will tell us how many elements it has in it, okay? Numbers.size is very much like the string.length. You just do it right there, and it says, okay, numbers is a vector, and see what's in there. So let's take a look and see what happens to the size of a vector that we haven't done anything to. The size is 0. Okay, well that's good. Well, one of the things we might choose is we might choose to give it some initial value. So we could say we're going to have, say, 5 things in there. Okay, and what happens when we run it like this? If we compile it and we run it again, it'll now say that there are 5 things in there. Well, it would be nice to know what those 5 things were. So let's write a little loop that does this. We can have an int position that starts at 0. And just like we did before, while position is less than numbers.size, we can see out numbers sub position. And I'll say sub like this when I mean things inside the square brackets. We can put out a space, or I'll just put an inline there. That'll be nicer. Okay. So here's our algorithm. We declare a vector that's going to hold doubles of numbers. We set it to have 5. We print out how big it is. We say we start at position 0, and while position is less than numbers.size, we output numbers.position, and then we increment position so that we go on to the next one. So let's make sure that compiles. We'll clear it, and we'll run it, and we say 5, which is the size, and then there are 5 zeros in there. Okay, which is nice, because it has defaulted to declaring things zeros. Now if we want, and most of the time we don't, but if we want, we can also put some other value in here. And when there are 2 things, and these things are called parameters, as we'll talk about later, the first is the size, the second is the default value. All right, we already saw that when we don't have this comma 1 right there, it defaults to 0. But if we compile it and we run it, we can see now that these things are all 1, because when we define this, we put a 1 in there. Since it's a double, we could put, pi in there if we wanted, and compile it and run it, and now everything is initialized to pi. Whatever we put in here is what gets initialized to. Okay. All right, we can ask the vector questions sometimes. We can do something like if numbers.empty. This checks if the vector is empty or not. We can see out numbers was empty. Okay, and I'll show you this code again. Numbers.empty. This is a method that calls and says, hey, if the vector is empty, output this. I expect when we compile this and output it, we will not see that because the vector is not empty. We did not define it to anything. So let's take that initialization out and see what happens now. Let's see if without the initialization, if that counts as it being empty. It is again not empty because we told it to have 5 spaces. Okay? Since we told it to have 5 spaces, the vector believes that it has 5 things in it. Hence, it's showing us the size of 5. But if we get rid of that 5 altogether, what you will see, whoa, is something unexpected. Oh, I got to get rid of those parentheses, sorry. What you see is when we run it now, the size was 0 and numbers was empty. Okay? So empty tells you how many slots the vector has that can hold something in it. And if you don't initialize it, it starts off absolutely empty. The other thing we can do, and we can go back here and put this 5, and I don't know, 3.14 was good for me, so we'll put that in there. What? Oh, sorry, wrong spot. That was not the initialization. 5, 3.14. All right, so that compiled cleanly. We had no problems. So if we run it now, what you'll see is we're back to 5 elements, each of which has been initialized to 3.14, and numbers is not empty. But we have this thing we can do. It's numbers.clear. And clearing should empty the vector. Okay, so here's our algorithm. We define a vector. We put 5 copies of pi in there. We start at position 0, while position is less than numbers.size, output the position, so and so on. Clearing it can clear, and if it's clear, we'll see it as empty. So let's see if this works. If this does what I expect, we will see that we get 5, 3.14, but numbers was empty at the end. And numbers was empty because we called numbers.clear. So this is kind of a brief example of how vectors work. They are super duper useful. And one of the things that we commonly do is print things out like this, right? This while loop we use to print things out. I'm going to make another file for us to work on. It'll be like this, and I want to show you a different type of loop. So far the only loop we've seen is the while loop, but I want to show you a different type of loop that is designed exactly for these types of situations where you have a vector or a string and you're trying to iterate across each and every item in there. So let me pause for a second and make a copy of this. So all right, so we now have this file vector4.cc, and what we're going to do is change this while loop into a for loop, okay? A for loop has certain elements about it that the while loop doesn't, okay? For loop has 3 things. It looks kind of like this. For, and you get what is called a start condition. You get, then a comma, you get an end condition, which is usually a Boolean. And I'm screwing this up, it's not a comma, it's a semicolon, end condition, and then an increment operator that happens every time. Okay, so the loop looks like this. There are 3 things: a start condition, an end condition, and an increment. Now the while loop we wrote already has all of these. This right here is the start condition. This right here, the inside the Boolean, is the end condition. And this right here is the increment step. Because these things are so common, we develop a special kind of loop for them. So I'm going to rewrite that loop above as a for loop. Okay, we're going to do exactly the same thing we did before, same loop, same functionality, but using a for loop instead. So here what I'm going to do, I'm going to say for, I open parentheses, int I equals 0, and I is going to be for index. It's super common for I to be index, and index is going to be the position in the vector. I less than numbers dot size, and then I plus plus. And what I'm going to do inside this loop is exactly the same thing we did up here, which is cout number position, except I changed position to I. Okay. So this loop right here, this for loop for in I equals 0, I less than numbers dot size, I plus plus, is functionally exactly the same as this loop up above. Okay, where you have int position is equal to 0. This is the start condition, just like that there. You have this end condition, which is numbers less than size. It'll keep operating as long as this is true. When it is false, it will stop, and we have that there as well. And we have the increment, which is plus plus. And we have that plus plus as well. And then we output I. Notice that even though I was defined in the loop right there, it is still valid. So let's just step back and look at our whole algorithm. We declare this vector, we have 5 things, we put 3.14 in there, print out the size. In fact, let's just put a little thing here that makes it clearer what we're doing. Then we use a while loop with this variable position to loop over and print everything. Then we're going to use this for loop. And I'm going to just label each of these so they're clearer. And we don't really need to empty out the vector and prove that it's empty anymore, so we'll take rid of that. Okay? All right, so while loop, for loop. Let's see if both of these things work. So compiled cleanly, we run it. Haha, it would actually help if I used vector 4, which is the correct program. All right, vector 4 worked, and let's run that one instead and make sure it does what we want. So size was 5. We have the while loop that prints out 3.145 times, and we have the for loop, which does the exact same thing. For loops, super duper common. In fact, are really, really common. Often much more common than while loops, right? Because there's going to be a lot of times that we have a string or a vector or a set of some kind, and we want to go through and look at every single thing in there. And the for loops are designed exactly for that. Okay? Start condition, end condition, all the way through. All right, let's look at some other for loops that do the same thing. So let's look at how to do, I don't know, a for loop backwards. Okay, for this one, we can say for int I equals numbers dot size minus 1, because if the size is 5, the highest one is going to be 4, so you have to take 1 out there. I greater than or equal to 0, I minus minus. In this case, our decrement is going down, and all right, I'm going to change our vector up here because it's not very helpful having all the numbers the same. So let's do this: numbers dot push back 1. This one's going to be 2. This one's going to be 3. This one's going to be 4. And this one's going to be 5. Okay. So now when we run, instead of getting 5 values that were all pi, we should see 1, 2, 3, 4, and 5. The size will still print out. It should print 5. The while loop should print 1 through 5. The for loop, that are super duper common, should print 1 through 5. And then the backwards loop should print out 5 down to 1. It should go backwards. All right, let's see if that's what we got here. And it's pretty bad that I named this vector 4. So, but. All right, while loop 1, 2, 3, 4, 5. For loop 1, 2, 3, 4, 5. Backwards for loop 5, 4, 3, 2, 1. All right. I'm going to rename this vector 4. I'm going to rename it if.cc. Whoa, hang on a second. Yeah, I didn't mean if. I'm going to make it 4.cc. So now we have one separate one for the for loops, so you can see how you loop over those. You're going to be using a lot of these. It'll be pretty clear. Remember the 3 things: an initial condition, termination condition, and an increment or decrement, some sort of change. Okay? Most commonly, they will look exactly like I have it right here. For int I equals 0, I less than some size, I plus plus, and while you're working over everything, do something for each loop. Okay, since we're talking about for loops, we might as well talk about one other kind of loop and then kind of contrast the different loops that we have. So there's one other kind of loop, and this loop is known as a do loop. And it looks like this: do something while condition, like that. And I'll give you a standard example of this, but this is the body of the loop. This is what happens inside the loop. And this is a condition that's either true or false. So let's do something like this. Let's say set I equals to 0, and sorry, wrong language, int I equals 0. And what we're going to do in here is we're going to see out angle, angle I, angle, angle ENDL, and then I plus plus. And the condition is going to be while I is less than 10. Okay, so here's our algorithm: set I equal to 0, output I, increment it, and keep doing this over and over while I is less than 10. So let's go over here, we'll compile it and make sure it works. And, oops, oh, sorry, I have an extra parentheses there, do while. There. So, sorry, I just had an extra set of parentheses around here. So you have do, angle brackets, while, and the condition I is less than 10. So, if we run this, we'll see it prints out 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And we can trace through this. So the first time, if we trace through this step by step, is int main. We start there. Int I equals 0. We go a step forward, get to the do loop. See out I. I is 0, so we output that in end line. And we do I plus plus. I plus plus turns 0 into 1. We say while I is less than 10, I is 1. Is 1 less than 10? Yes, it is. So we go back up to the top of the do loop and we output I, which is 1. We increment 1. Now it's 2. 2 is less than 10, so we go back up to the top. We output 2, increment 3. 3 is less than 10, go back up to the top. Output 4, increment it to 5. 5 is less than 10, and so on. Eventually what happens is I will be 9. We'll output 9. It'll become 10. It will say I less than 10. Well, 10 is not less than 10, so it will stop and return 0. So this counts out every number less than 10. Okay. Now what's interesting about this is we can compare it with a while loop, right? So we could also do the same thing. We could say I equals 0 while I is less than 10, and have the exact same body of the loop. The body again is what happens inside the curly brackets or in every single time the loop goes. And in this case, we might see the same thing, right? We'll see I is 0 and all the way up. So what we should see now is, because let me just stop for a second, and I'm getting ahead of myself. We have the do loop like we saw before, and now I've reset I to 0, and I've added a while loop. The while loop has the same termination condition, while I is less than 10, and outputs exactly the same thing, which is I, and increments I. So what we should see is this one do 0 to 9, and we should see this one do 0 to 9. Let's just see if that works. Whoops. So here we have the first part, 0 to 9. Here we have the second part. Both loops do the same thing. In this case, they do exactly the same thing. They both print out things from 0 to 9. But I want to emphasize one important difference between the two things. If we set I to 10, and I'm going to see out which loop we're doing so we know. Oops, while loop. Okay? If we see out I equals 10, you will see that the do loop and the while loop are quite different. Here's why they're different. They're different because the do loop always does what's inside the curly brackets at least once, even if this condition is not true. The while loop, on the other hand, will not do the body of the loop unless the condition is true when it starts. So here's what we should see. We should see this thing print out 10, go to 11, and then stop. This one we should see print out while loop. It should be 10. It's not going to print out anything. So if we recompile this, we will see the do loop prints out 10. The while loop doesn't print anything. Okay? The do loop is very useful if you want to make sure the thing that happens inside the loop always happens at least once. Okay? The while loop is useful if you want to be able to make sure that the stuff inside the body does not happen if you don't want it to happen initially. It is actually possible for any loop, like a while loop or a do loop, to be rewritten in a way that makes it equivalent to any other loop. And it's not that challenging for once you've been doing this for 20 years. But the thing to remember, do loop always does the body at least once, while loop may not do the body the first time. Okay, I covered a lot of material on this stuff. I went a little bit faster because I know you're watching on video, and I'm hoping that you can go back and take a look as needed. I will talk about some different stuff in class tomorrow that doesn't depend directly on this, in case you don't have a chance to watch it before class, which would be perfectly natural. You will need to watch it before the exam. And of course, if you've reached the end, then you're already watching it before the exam, so I don't even know why I'm saying this, but this stuff is on the exam. Good luck. I hope you learned something, and please bring any questions you have to class on next Monday, which should be the 23rd, I believe.